All right, people, welcome back. So here we are again with our journey in dynamic programming. And in today's episode, we're dealing with problem 62, unique paths. So this feels like an interesting problem, as you can see here from the graphics. So there is a robot on a m times n grid. The robot is initially located at the top left corner here, grid 0, 0. The robot tries to move to the bottom right corner, which is m minus 1 and minus 1 in the index. The robot can only move either down or right at any point in time. Okay, so we can move here, 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 here. The test cases are generated so the answer will be, given, of course, I was missing a piece of the trace. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. Interesting. This feels a very mathematics problem. The test cases are generated so that the answer will be less than or equal to 2 times 10 to the 9th. Okay, so let's see, for example, this is the robot, okay? So we have two chances, like we have two possible moves when we start. Either we go down or we go to the right. And once we are here, for example, we have again two choices. Either we go to the right or we go down. So let's say that we go down. And again, two choices, okay? So let's say that we go to the right. And again, two choices. And this until, for example, we go down here. And now we just have one choice, right, 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 okay? Or, on the other hand, suppose that you go right, 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 until now we have two choices. But once you're here, you can just go down, okay? So it feels like we always have two choices until we reach index m minus 1 or n minus 1, okay? When we reach index m minus 1, for example, we have to continue only in the other direction. So there are 28 possibilities. And with m equal to 3 and n equal to 2, there are just 3 possibilities. Okay, so you should imagine a box like this. So you can go either this way, and then you go there. You can go this way, or you can go this way. Okay, these are the 3 possible paths that are coming to it at the moment. Okay, good. So how should we output the total number of paths? For sure, we need to use a dynamic programming approach. Okay, so just one idea. Of course, each time we compute a path, that path has the same number of steps, which, for example, let's say this case is 1, 2, 3, 4, 5, 6, 7, and 8, while in a case with 3 by 2 will be 1, 2, 3. Okay, so I guess we can compute the total number of steps one have to do as m plus n minus 2, right? Okay, let me think. Okay, so let's try to add one more cell in the grid, and then we see if we can reach like the end with the dynamic programming approach. So let's say, for example, that the grid is composed by just one cells. So there will be just 2 cells, sorry. So there will be 1 as the only possible path. Let's say, for example, that you add 1, there will be, again, just 1 step to do. And this will be true unless we add a new value. So, for example, let's say that now we have a 2 by 2 grid. In this 2 by 2 grid, there are 2 potential paths. Now, if I add 1 in this direction, we will have 3 potential paths. If I add another 1, I get, what's that? It's 1, 2, 3, 4, 5, 1, 3, 3. There are 4 possible paths, and I suppose if I add a 5th one, there are 5. Now let's say 1, 2. So in a 3 by 3 grid, I've got 1 path, 2. So here in a 3 by 2 is you have 3 paths with respect to the 2. And now if you add another 1, you've got 1, 2, 3. You have 6, don't you? Yes, you have 6 possible paths. I don't know. I don't really know. Hints? No hints? Good. Fantastic. 1, da. How many did I get? The first, second, third, fourth, fifth, 1, 4. I don't know, guys. I'm counting the paths, but I'm not spotting an easy. Also because, like, I'm looking for a closed form formula, but it doesn't work because I think we have to use a dynamic programming approach. Okay, maybe we can approach it like I was trying to find dynamic programming combinations, but at this point, guys, I think we have to think differently. So let's use this figure. We know that the number of steps we have to make are m plus n minus 2. We said that, right? So actually, in terms of the number of steps, in this case, we have to make 2 steps down and 6 steps to the right. Okay, so it feels like okay. No, I think we can solve it easily because we have 2 steps down and then we have right. How many are these? Just 5, and we have to do 6. So now the question is, how many permutations of this can we make? Is really just that? That would make it extremely easy to solve. And I don't understand where is the dynamic programming approach. But yes, that's probably the best way. So it would be something like I've got m and n. So the way I do the permutation is basically, let's say that I have to do a permutation of 2d and 6r. Then I actually have to do 8 factorial divided by 2 factorial because I have to d divided by 6 factorial. This is the way you calculate all the possible permutation of this string. And then apparently you get to all the, like it must be that. I think we can do, I think we have to import math for that. And then we can do something like result is equal to m plus n minus 2, like factorial of that, divided by factorial of m minus 2. Let me use parentheses, times factorial of n minus 1, sorry, 1 and 1. And that's it actually. And then we return result. And it should be it. Instead it's not correct. You want it to be an integer, which is fair. And it's incredible. No way, guys. Like I can't believe. Okay, now you should tell me, where is the dynamic programming? Where is it? Tell me. Literally, we can solve this in one line. It's literally a permutation. Tell me, where is the dynamic programming approach? Or is this not efficient? Is this not efficient? Is this the reason why this is not the best approach and we should look for another approach? So this in principle is like has complexity m plus n, because with factorial we are actually multiplying each number from 1 to m plus n. And also this, but this get like absorbed by O m plus n. The only reason why we may wish to use a dynamic programming approach is to make it like memory wise it's all 1. So the only thing that changes is actually the time complexity, which now is m plus n. We can now make it more efficient by using a dynamic programming approach. I don't know, guys. At this point, here is what I'm going to do. I'm going to go on Google and see if there is anything, any better solution for that, and I will come back to you to explain what I found. Okay, guys. So apparently, I found that this solution is okay. Actually, it's a more efficient dynamic programming approach. But we will encounter problems in the future, maybe the next ones that we were going to deal with, for which this solution will not work. That's the thing. But this is fair. So in my opinion, we can stop here with this problem. And once we will meet another dynamic programming approach can be just solved, like another problem that can be only solved with dynamic programming, we will use dynamic programming with that. But I think we must defend this solution because it was good. So guys, thank you very much for joining me in this video and see you in the next episode.